Section: Introduction. In this section, we discuss the significance of music as a cultural expression and its connection to human experiences. We explore the innovative task of converting text descriptions into music, which opens new possibilities for multimedia creation. Recent advancements in generative models have greatly improved this process. Traditionally, text-to-music generation has used language or diffusion models to create audio representations. Among these, diffusion models have proven effective in handling complex data like music by reversing the transformation from structured data to random noise. As the diffusion process is iterative and computationally intensive, researchers are focusing on more efficient training methods and faster sampling techniques, such as distillation. One promising approach is the rectified flow, which connects data and noise along a straight path, enhancing training efficiency and generative performance. While this method has shown success in image generation, its use in music creation is still largely uncharted. In model design, conventional diffusion models often rely on U-net structures. However, these models struggle with capturing spatial correlations in signals. Transformer-based diffusion models have addressed these issues by treating images as sequences and using stacked transformer blocks for noise prediction. The integration of cross-attention for text has set this method as a standard for generating high-resolution images and videos from text descriptions. We introduce FluxMusic, a new framework that applies rectified flow transformers to noise predictive diffusion for text-to-music generation. This framework operates in the latent space of MEL spectrograms. Building on the text-to-image FLUX model, we present a transformer architecture that uses dual attention streams for music and text, allowing for effective information flow. After processing, we focus solely on the music stream for noise prediction. We utilize various pre-trained text encoders to extract features and enhance inference. Coarse textual information is combined with time-step embeddings for modulation, while detailed text features are integrated with the music sequence. We train our model using the rectified flow approach and assess its scalability. Our comprehensive analysis compares our method to existing diffusion models, highlighting its training efficiency and performance improvements. Our main contributions include introducing a FLUX-like transformer architecture for text-to-music generation with rectified flow training, marking the first application of this approach in this field. We conduct a thorough system analysis, covering network design and parameter scaling, demonstrating the advantages of the FluxMusic architecture. Our extensive experiments show that FluxMusic performs comparably to other recent models based on both automated metrics and human evaluations. Finally, we make our results, code, and model weights publicly available to encourage further research. In the realm of text-to-music generation, we note that previous methods have mainly used language or diffusion models to create music that aligns with descriptive text. Models like MusicLM and MusicGen generate waveform representations, while others like MuSci and Audio LDM focus on MEL spectrograms. Our approach also models the MEL spectrogram within a latent VAE space, contributing to this evolving field. Section Summary. In this section, we introduce FluxMusic, a novel transformer-based framework for text-to-music generation that utilizes rectified flow training to enhance efficiency and performance. We also compare our approach with existing models, demonstrating its competitive generative capabilities and making our results, code, and model weights publicly available for further research. Section: Diffusion Transformers. In this section, we discuss diffusion transformers. The transformer architecture has shown great success in language models and has also proven effective in various computer vision tasks like image classification, object detection, and semantic segmentation. Building on this success, we have developed the diffusion transformer, which replaces the convolutional U-net backbone with transformers. This change allows for better scalability and easier parameter expansion compared to U-net diffusion models. We have particularly noticed this scalability advantage in areas such as video, image, and speech generation. Recent works like Macon Audio 2 and Stable Audio 2 have also utilized the DIT architecture for audio generation. In our work, we focus on a new multimodal diffusion transformer structure similar to FLUX, which we optimize using rectified flow. Our methodology, FluxMusic, is a straightforward extension of FLUX aimed at generating music from text within a latent space. We will first review rectified flow as it applies to diffusion models, then examine the architecture of each component in detail, and finally discuss model scaling and data quality. Regarding rectified flow trajectories, we explore generative models that create a mapping from samples drawn from a noise distribution to samples from a data distribution using ordinary differential equations, ODE. We express this connection through a velocity parameterized by a neural network's weights. While directly solving this can be computationally heavy, we find a more effective approach is to regress a vector field that defines a probability trajectory between the two distributions. We consider a forward process that transitions from the data distribution to a standard normal distribution. This is represented by a combination of the original data and noise. We can then construct a marginal vector field that generates the probability paths using conditional vector fields. For our model architecture, we integrate both text and music modalities to enable text-conditioned music generation. We utilize pre-trained models to create suitable representations and detail our FLUX-based models architecture. In terms of music compression, we convert each 10.24-second audio clip into a MEL spectrogram and then compress it into a latent representation using a variational autoencoder, VAE. This latent representation is crucial for adding noise and training the model. We also use a pre-trained hi-fi GON to reconstruct the audio waveform from the generated MEL spectrogram. For music generation, our architecture builds on the MMDIT and FLUX frameworks. We create an input sequence that combines text embeddings and noised music representations. We flatten the noised music representation into patches and align it with the text encoding before concatenating the two sequences. We then process this through double stream and single stream blocks. In the double stream block, we use separate weights for text and music, allowing them to function independently while still interacting during attention operations. The single stream block focuses solely on music modeling. We also incorporate embeddings of the time step and text into the modulation mechanism, using multiple text encoders to capture different levels of information. This approach enhances model performance and flexibility during inference, allowing us to use various subsets of text encoders and pre-store blank representations to streamline the process. Section Summary. In this section, we discuss the development of the FluxMusic model, which integrates text and music modalities for text-to-music generation using a rectified flow approach. We detail the model architecture, including the use of variational autoencoders for music compression and a dual-stream transformer design that allows independent processing of text and music while facilitating their interaction during generation. Section: Model at Scale. In this section, we outline the key hyperparameters of our FluxMusic architecture, which include the number of double stream blocks, single stream blocks, hidden state dimension, and the number of attention heads. We explore various configurations of FluxMusic, ranging from 142 million to 2.1 billion parameters and from 194.5 billion to 2,928 billion floating point operations, allowing us to thoroughly assess the model's scalability. We calculate the GFLOP metric for generating 10-second music clips based on text input using a specific patch size, utilizing the THOP Python package. We recognize that using synthetic captions can significantly enhance the performance of generative models, similar to text-to-image generation. Therefore, we incorporate enriched music captions generated by a fine-tuned large language model, specifically the LP Music Caps model from Hugging Face. To ensure a balanced input, we mix 20% original captions with 80% synthetic captions, reducing the risk of the model overlooking concepts not included in the music captioner's knowledge. Our datasets include several sources such as Audio Set Music Subset, Magna TagTune, Million Song Dataset, Free Music Archive, Music for All, and a private dataset. We segment each audio track into 10-second clips, sampled at 16 kHz for consistency. Detailed captions for these clips are sourced from Hugging Face datasets, and we also label additional music data using LP Music Caps models, resulting in a comprehensive training dataset of approximately 22,000 hours of diverse music content. For benchmarking, we evaluate our Music FLUX model against the Music Caps dataset and the Song Describer dataset, which provide high-quality music descriptions. In terms of implementation, we use the last hidden state of FLAN T5XXL for fine-grained textual information and the pooler output of CLAP-L for coarse textual features. Our training involves 10-second music clips sampled from full tracks, with a batch size of 128, a gradient clipping threshold of 1.0, and a learning rate of 0.0001. During inference, we apply a rectified flow with 50 steps and a guidance scale of 3.5. To maintain model stability, we keep a secondary copy of the model weights, updated every 100 training batches using an exponential moving average. For unconditional diffusion guidance, we set the outputs of each text encoder to null with a 10% probability. We evaluate the generated results using several metrics, including Frechet audio distance, Kullback-Leibler divergence, and inception score, all calculated with the audio LDM_eval library to ensure consistency. To analyze the effectiveness of our approaches, we conduct ablation studies on specific components while keeping others constant, using a subset of the training set and an out-of-domain evaluation set. Finally, we investigate the architectural choices for the diffusion network in FluxMusic, comparing two variants, one using only double stream blocks and another combining double and single stream blocks. We test a smaller model version with configurations of 15 double stream blocks and a mix of 8 double and 16 single stream blocks, resulting in similar parameter counts. Our findings indicate that the mixed architecture accelerates training and improves generative performance, leading us to adopt it as the default configuration. Section Summary. In this section, we detail the hyperparameters and configurations of the FluxMusic architecture, which ranges from 142M to 2.1B parameters, and we incorporate synthetic music captions to enhance model performance. We also describe our dataset preparation, evaluation metrics, and the advantages of our architectural choices, highlighting that a mixed structure of double and single stream blocks improves training speed and generative quality. Section: Effect of rectified flow. In this section, we present our findings on the effects of rectified flow and model parameter scaling in FluxMusic. We compare various training strategies, including DDIM and rectified flow, using a small model version with a batch size of 128 and 200,000 training steps to keep the computation cost consistent. As expected, and consistent with previous studies, we find that rectified flow training positively influences generative performance in music. Next, we explore how the scaling of the FluxMusic framework affects performance by analyzing model depth and width. We train 4 versions of FluxMusic on 10-second clips, with configurations ranging from small to giant. Our results show that increasing the depth of the model from an 8:16 ratio to a 16:32 ratio, as well as expanding the width from 512 to 1408, leads to improved performance. Although the model has not fully converged after 200,000 steps, we observe significant performance gains at all training stages as we increase both depth and width. We also compare our Music FLUX method with several established text-to-music approaches, such as Audio LDM2, MUSI, Gen 1, QAMDT, Music LM, and Music Gen. Our results, summarized in a table, demonstrate that FluxMusic achieves state-of-the-art performance across various metrics, highlighting its scalability as model and dataset sizes grow. While we see a slight edge in FAD and KL metrics on the Song Describer dataset, this may be due to the dataset's limited size. Our superiority in text-to-music generation is further supported by subjective evaluations. For human evaluation, we assess the performance of our text-to-music generation based on overall quality and relevance to the textual input. Raters score the audio samples on a scale from 1 to 5, and our evaluation team includes both expert music producers and novices. Each audio sample is rated by at least 10 individuals to ensure reliable results. Our findings indicate that FluxMusic significantly improves both the overall quality of the music and its alignment with the text input, thanks to the RF training strategy and our model's advanced architecture. Expert feedback highlights substantial gains, suggesting the model's potential value for professionals in the audio industry. Finally, we visualized generated music clips based on different prompts and perspectives, including variations in training steps, model parameters, and classifier-free guidance settings. The results are illustrated in several figures, and for more examples, we encourage visiting our project webpage.